Okay, first thing we want to note is that I wrote down V here, just being careless, and that doesn't work at all. It's V to the 1.4. Again, the reasoning being that pressure times volume to the 1.4 is constant, so that PV to the 1.4 equals P2 V2 to the 1.4 for any state of the system during the adiabatic expansion. So that when we do the integral now, we're going to be integrating this expression P dV between V2 and V3. And that's V2 and V3. I'll have to change that over here. I wrote something down that's not quite right. Okay, so we have then the P2 V2 to the 1.4 comes out of the integral being constant, and we're then integrating from volume 2 to volume 3, volume 2 being 0.56 liters, volume 3 being 0.6 liters of dV over V to the 1.4. And that should be very clear. You probably should have written out that integral yourself just to see how it works out. But one way or another, understand this. Okay, well, the integral of dV over V to the 1.4 is what? It's going to be V to the negative 0.4 times the reciprocal of negative 0.4. Reciprocal of negative 0.4 is negative 2.5. The negative here, 2.5 here. We get this expression. Here's V2 and V3, 0.56 liters and 0.6 liters. We bring that up here, and I miswrote one thing here. This should be V3, this should be V2. But I'm just rewriting, except I'm using the V3 and V2 instead of the 0.56 liter and the 0.6 liter, just to illustrate these expressions. Okay, so we have volume to the negative 0.4, volume to the negative 0.4. The difference is going to be volume to the negative 0.4, which is multiplied by volume to the 1.4, giving you just a volume to the 1. Okay. Now, if we do the units and the numbers, you can work these out yourself. P2 V2 to the 1.4, using P2 110 kilopascal, V2 0.56 liters. Plug that in, we get 50 kilopascal liters to the 1.4. On the V3 to the negative 0.4 minus V2 to the negative 0.4, our units are going to be liters to the negative 0.4. If you put in the 0.56 liters for V2 and the 0.6 liters for V3 and do the numbers, you get approximately 0.034. That's liters to the negative 0.4. I didn't do that one in my head. I relied on Excel to do that calculation for me. But then when we multiply these, 50 times 0.25 times 0.034, the numbers come out 4.1. And that's going to be 4.1 joules, because if we multiply liters to the negative 0.4 times liters to the 1.4, we get liters multiplied by kilopascals, as we've seen repeatedly, gives us joules. So we have 4.1 joules, and that's the work done by the expansion. Now, that should match something over here. Okay? We could calculate T3. Now I've just written out the basic calculation of T3, and I did these in my head, and I was off by a little bit. But the T3 is going to be pressure ratio times volume ratio times T2. Pressure ratio, P3 over P2, is 100 over 110. We start at 110, we end up at 100. And 100 over 110 is about 0.91. V3 over V2 is 0.6 over 0.56, which I estimated to be 1.06. It's actually 1.07. Using these numbers, I estimated the temperature to be 358 Kelvin. The 1.06 should have been 1.07, and the 358 should have been 360. Rounded to the nearest whole number. Okay, so that wasn't too far off in the estimate, but this is more accurate. We want to use the more accurate up here, because what I want to do is figure out the change in internal energy. Change in internal energy is very easy. We just multiply the number of moles by the number of degrees of freedom times 1/2 R. 5 degrees of freedom, just as before, times the delta T. We have approximately 0.02 moles, approximately 21 joules per mole Kelvin, and a negative 10 Kelvin temperature change, giving us negative 4.2 joules. Now, how does this compare with this? This number and this number, within round-off errors and approximation errors, are identical, being equal and opposite, of course. Why is that? Well, it's because in the internal expansion, in the adiabatic expansion, there was no thermal energy, no heat energy supplied to the system. The work of expansion, which is this, is 4.1 joules. The only place for that work to come from was from the internal energy, which we see decreased by 4.2 joules. And this should bring everything kind of closed circle. I might add one comment here. Okay, the one comment, I went ahead and wrote it off screen, or off camera. Delta Q23 is 0. We know that because this is an adiabatic expansion. So delta U23 plus delta W23 had darn well better be 0. Well, delta W23 is 4.1 joules approximately. The delta U23, let me put the 23 here, is negative 4.2 joules approximately. Within round off, those add up to 0. And that confirms the validity of this analysis, and we can be pretty confident in the whole thing.